Okay, so what wanted to do today was to basically finish the angular momentum discussion we started the last time and then talk about symplecticity. But so first, let's just kind of get into it. As a warm-up, let's just quickly recap our assumptions. So now we are working with a 3D system, like you would typically be working in a 3D graphics and animation. So that means that you have 3D particles with positions that would be called xi, so that's a 3D vector, and velocities, vi. So that means that, and this I goes from 1 to some m, where m is the number of particles. So the number of degrees of freedom n will be 3m, and the phase space dimension is 2n, which is 6m. Okay, so that's the dimension of the phase space. So when we are writing these z vectors, they will be 6m dimensional vectors. That's our notation for the phase space vector. Now we are assuming, and here what I mean by the assumptions is assuming that each point has unit mass. So mi is 1. The mass of every point is 1. I explained you the last time why that's an okay assumption if we just assume the masses are not changing, which is often the case in physics-based animation. Okay. In that case, that means that the kinetic energy function is very simple. It's just 1/2 of the norm, square norm of v. And we also assume that our potential is only position dependent. So the potential function is only dependent on this x thing, where the x are the positions, the vector of all the positions. So the x is a 3m dimensional vector, as you remember. And so that also encompasses the assumption that the forces are conservative. And also they don't depend on time, because here you don't have any time dependence. It only really depends on x, which is again the typical case. All right, so what we talked about the last time is we talked about first integrals, which is a different word term for conserved quantities, right? We said that a function from phase space, a function from phase space to scalars is a first integral if and only if the gradient of the function transpose the J matrix, the Poisson matrix, times the gradient of the Hamiltonian is 0. That's how we defined the first integral last time. And what we showed is that the Hamiltonian itself is an example of first integral that proves energy conservation under these assumptions. And we also discussed linear momentum conservation. Just to make sure you remember that, what was the assumption necessary for linear momentum to be conserved? So we said that the Hamiltonian is always a first integral, as long as we have this assumption that the potential is dependent just on x, not on t, okay? But linear momentum is not always conserved. It's only conserved sometimes, and what this sometimes was, do you remember? Okay, maybe raise your hand, because then I will really not be able to make it out who is speaking. Okay, someone? Sorry? Oh, and don't be shy to yell, because I really don't hear. Fixed rotation? No, linear momentum, not angular momentum. We'll do angular momentum in a second. What is the assumption needed for linear momentum to be conserved? Trevor? Exactly. Yes. So the potential needs to be invariant to shift or translation. Exactly. And depending on what translation is it invariant to, that determines what momenta will be conserved, what linear momenta will be conserved. Okay. And what I want to do today is, so the linear momentum is was an easy example, because then the first integral was a linear function too. So what I want to finish today is the example of angular momentum, which is a little bit trickier, but it's another very important quantity conserved in nature. Okay, so let's talk about angular momentum. And the assumption necessary for angular momentum to be conserved is rotation invariance of the potential function. Okay, so what I mean by that mathematically is that's what we are talking about the last time, is that the potential needs to be invariant to rotating the entire vector of positions, where this Q alpha matrix, this thing here, that was a rotation by angle alpha about the x-axis, okay, and rotating every single point x individually. So if you remember, there was this large block diagonal matrix. So that means so I guess the easiest way to think about it, if you have like a big system, if I have some axes here, maybe some x, y, and z, right? And then I have some object which is modeled as a collection of particles which are connected in some way, either using finite elements or using springs. This is something we'll talk about later. Then this says that that potential does not change if we rotate all of the points by the same amount about the x-axis. Okay? So a typical example would be if we said that the gravity is pointing in the direction of the x-axis, okay, we can choose the axis arbitrarily, right? Usually we do the y-axis for gravity, but we could do the x-axis, no problem, right? So then if you have any free object in the gravity field, then the potential will be invariant to rotations about the direction of the gravity, right? Because the gravity potential is linear, at least the simplest approximation of gravity. But again, that's almost exclusively what we used in physics-based animation, right? If you were doing astrophysics, you would be doing different gravity things, eventually be doing relativity. But here we just use the linear gravity potential. Brian, you had some question?
Yeah, are you referring to like a circular orbit in this situation?
If I'm referring to circular orbit, what do you mean by circular orbit? I think I am, but let's clarify that.
Yeah, so like think of, in astronomy we've got Earth rotating, so it's a circular rotation. That's similar idea of what you're referring to.
That's right, yes. So that's the idea behind angular momentum, and also the related property of the potential being invariant to rotations, right? Like as a good example, good motivation for the angular momentum is a figure skater, right? Or even a person rotating, swiveling about its own axis, because the direction of the gravity points up, right? So if you are rotating about that, you are not changing the potential of all these individual points in the gravity field, right? And that's what will lead to momentum conservation, and that's what I will show you mathematically. Okay, no hand waving, hard math formulas. Okay. All right. So the last time what we did, we took this expression and we said that if this is true for every alpha, then from this it follows that this sum over I, where I goes over all particles, so let me write it nicely for now, from 1 to m. So the gradient with respect to particle number I of the potential, okay, transposed S1 and Xi equals 0. Or let me remind you, the S1 was this funny matrix we derived the other day. 0, 0, 0, 0, minus 1, 0, 1, 0. Okay? So just so this S1 is this matrix, a 3 by 3 matrix. The Xi, that's the position of the particle number I, so it's a 3 by 1 vector. And this is the gradient of the potential with respect to the ith particle. So that's the negative force acting on particle number I, and since I transpose it, it's a 1 by 3 vector. Okay? So altogether, this produces a scalar, and this says that if I sum all the scalars, I get 0. Okay, that's what we ended with the last time, and that involved differentiating this by alpha and massaging this until you got this expression. Okay, that's what we did the last time. You remember that? And also, it's good to remember what the S1 thing was, what the S1 thing does. That's kind of important, so let me recap that again. So if I have 3D vectors A and B, ATS1B, do you remember what this thing was? It's a scalar, right? And what does that scalar mean? So let's quickly rederive that. So if I take it as A1, A2, and A3, what you need to do is to just write it out, right? So then I put the S1 here, then I do B1, B2, B3. So now then I just do the matrix products, right? So we can do the 2 in your head. So here you will get 0 minus B3 and B2. That's S1 times B. And that equals, what does that equal? A3 B2 minus A2 B3. That's what we also did the last time, and we also said this is the first component. What's that? Cross product, yes, yes, yes. Um, so that's the actually with a minus sign, minus first component of A cross B. Okay, the minus sign doesn't really matter because this thing equals 0, so feel free to multiply the whole thing by -1 and nothing really changes. Okay. All right, so this is what we did the last time, and now what I would like to do is to show you how this implies that the angular momentum is conserved and what it even is angular momentum. Okay, so angular momentum is another example of a first integral. Okay, and the angular momentum is, I will call it L. And I'll give it 1. Oh, by the way, that's also why I give it 1 to sort of indicate it's about the x-axis. Okay. 1, 2, 2 would be y-axis, 3 would be z-axis. So analogously, the angular momentum corresponding to the x-axis, I'll denote as L1. And it's a first integral function, so it's a function defined on phase space. And it's defined like this. It's defined as the sum over all particles, I, xi transposed the S1 matrix times vi. Okay? So you, of course, remember that the z is a 6m-dimensional vector stacking all the positions x and velocities v, right? So this is a well-defined function. So the xi and di are all 3D vectors, right? And then what I claim is that this is a first integral if this is true, if the potential is rotation invariant about rotations with respect to the x-axis. Okay? I guess better way to be. If the potential is rotation invariant about the x-axis, then L1 is a first integral. Okay? So let's prove this. So copy it. Drag and copy it. Copy. Paste. No. Ah, there we go. All right. So how do we prove this? So you remember, so this is how we said the first integral is, this is the condition that needs to be true if the function f, in our case L1, is to be called the first integral, if it's really an invariant of motion, okay? So the first thing is we need to do the gradient, okay? So first thing we should check the types, right? The types are fine because the z is a 2n dimensional vector, right? When n in our case happens to be 3m, that's all cool. And it returns a scalar, right? Because this thing is a sum of scalars, so therefore a scalar, okay? So syntax check, okay, like compile in your brain, or type check at least. So the next thing we will need is the gradient of L1. So let's figure out what the gradient of L1 is. So help me differentiating this. So to get the gradient, we need to differentiate. So the z is a stack of x1, x2 up to xm, then v1, v2 up to vm, right? That's how we said it's a convention, how we stack the degrees of freedom in the z state vector. So the gradient means differentiating with respect to all of these things, okay? So that means that first we differentiate with respect to the xi's, okay? So we are differentiating this expression first with respect to x1, okay? So what do we get? So it's going to be a long vector. And the first, do you know what that's going to be? So differentiate this expression with respect to x1. It's kind of simple. It's already there. No, yeah, that's a good point. 1, 1, 1. That's what it was the case in the linear momentum, right? And that's a great point. I'm glad you brought it up because that's how this is different from the linear momentum case. That's actually why I'm doing it, except that I forgot to mention it. The linear momentum was a linear function, so the gradient of that was a constant. So you got these ones and zeros there. Now the angular momentum, notice, maybe this is the first thing we should have noticed, what type of function is this? In linear momentum, this function, the first integral was a linear function, okay? This is no longer a linear function, right? Why? And how would you call it? Because what happens here is you are taking the axis and you're multiplying them with the v's, okay? Both the axis and the v's, they come from your z, from your argument, okay? So this you could call it a quadratic function, okay? Definitely not linear. So that also means that the gradient is no longer going to be constant because only linear functions have constant gradient. So that means that the gradient will also depend on the xi's and vi's, okay? And if you remember from calculus that the gradient of a quadratic function needs to be a linear function, that already gives you a clue how it should look like, right? James?
So why would you expect it to be a quadratic function and not like a sinusoidal function?
Oh, I mean, this is how I defined it, right? So that this S1 is a constant matrix, right? It only has zeros and ones in it. So this is really just multiplication of and summation of components of x and b. I could even write it out if you wanted, right? That would basically be just repeating this with the xi's and vi's, right? This a basically plays the role of x and the b plays the role of v, right? So I multiply the two together. That's where the quadraticity comes in because I multiply them together. And the rest is just summation and negation. So that's what I mean by quadratic. Quadratic function takes its arguments, multiplies them together, and that does some summing over that, right? All right. So the derivative, so that the gradient with respect to xi will be s1v1. Okay. The gradient with respect to x2 will be s1 v2 and so on up to s1 vm. Okay, that's the last one. And now I'm differentiating with respect to the v1 until vm. Okay, if you want, you look confused, so I will I will write one more step in between to make it a little bit more clear what I'm doing here, okay? So this is the gradient by x1 of L1. This will be the gradient by x2 of L1 up to the gradient of xm L1. And now I'll have the gradient by V1 up to the gradient by Vm L1, okay? So at this point here, I'm done differentiating by the positions, and I need to start differentiating by the velocities. And that's where it gets just slightly tricky, because for that I need to transpose it. I basically need to flip it to the form where I have vi transposed s1 transposed xi, okay? Because then if I do this, then the derivative by vi will be simply s1 transposed x1 up to S1 transpose XM, okay? That's again because I differentiate this by the VIs, what I get is this thing on the right, okay? That's basic vector calculus. If you are confused about this, the best way to get deconfused is to write it out by coordinates, okay? All these things, the VI, XI are just 3D vectors. So if you are unsure about this, that as a homework, write it in terms of coordinate x, y, z, and do the partial differentiation by individual scalars, okay? And you will see that this is indeed true. Maybe I will do a lecture if we will see it's useful on like a multivariate differentiation. Maybe later when we get to finite elements, there it gets actually trickier, the differentiation. So maybe that will be a good time to revisit this. So this is kind of easy. So the one thing we need to notice is what is the transpose of S1. So the S1 was this matrix, right? And you can see that its transpose will have a funny property, which even has a name. Do you know what that property is? Let me write it here. S1 transposed is what? Maybe raise your hands because I cannot make it out. Yeah, someone? Yep. And 0 minus 1, 0. That's right, Simon. So you can also write it as actually minus S1. Okay? So that's an anti-symmetric matrix. And that's no surprise because anti-symmetric matrices and cross products are intimately related. Okay? So I can use this here. I'll just copy the first part, S1VM. And this is just minus S1x1, and this will be just minus S1xm, okay? Because the transposition, all it does, it really changes the sign at the end of the day, okay? All right, so that's the gradient. And what do we need to prove now is that if I take this gradient, and let me write it down. If I take the gradient of L1, at any point z, let me not write this z there anymore, I transpose it and I hit it with the J matrix and the gradient of the Hamiltonian, then I would like to prove that this whole thing will evaluate to 0. Okay, because if I prove this, I've proven that L1 indeed is a first integral, of course, under these assumptions. Okay, so let's do that. So if we transpose the gradient, then this thing, so S1 V1 transposes to V1 S1 transpose, right? We know already that S1 transposed is nothing but minus S1, so I can write this as minus V1 transposed S1, okay? Then I will have minus V2 transposed S1 and so on up to V minus Vm transposed S1. And then the same thing with the x's, okay? So that will be x1 S1. So now there is no minus because the minus was already there. So these two minuses cancel. Okay, so again, I transpose the whole thing. I get x1 transpose, S1 transpose. S1 transpose is minus S1, but there already was a minus, so that minus goes away. Okay, there is, I'm missing a transpose. X2 transpose S1, and so on up to XM transposed S1. Okay, so that's a very long a gradient of the L1 transposed. Okay. And then I am multiplying it by this thing, okay, by the J gradient of H. And that you remember from before what we said this was, right? And this is another long, this time column vector. And that's the first thing is the stack of the velocities. And the second thing are just the partial derivatives of the potential. It's supposed to be with minus? Yeah, these guys are supposed to be with minus, right? It will not matter at the end of the day because, it will not matter at the end of the day, but yeah, it's there with minus. Is this clear, or do you need some more, any questions?
That vector represents J gradient H?
That's right, yes. J times the gradient of the Hamiltonian. So that's the right-hand side of the equations of motion Hamiltonian form. All right, so now I have two, so this is a dot product basically, right? It's a row vector times column vector, so that's a dot product. So all I need to do is to figure out what this dot product evaluates to. So the first part of the dot product, by the first part, I mean these guys dot producted with these guys, okay? And the second part will be these guys with these guys, okay? So the first part is minus Vi transposed S1 Vi. That's the first part, right? And the second part is Xi transposed S1 1 with also with minus, and now is the gradient with respect to I of the potential. Okay. And now let's think. Is that clear? So just writing the dot product as two sums, as a sum of two sums. All right. So let's figure out what these things are. So first, what is this? Okay. Any ideas? What does that evaluate to? I think I heard the right answer, but I am not entirely. So notice that you have the same vector vi on the left and on the right. Okay. You know, if you do cross product of the vector with itself, a cross a, what do you get? 0, right? So indeed, you get 0 here, right? I can show it from first principles, right? If I have, let's call it x, y, z, right? Then I have the S matrix, which looks like 0, 0, 0, 0, 0, minus 1, 0, 1, 0. And then I have the same x, y, z here. If you just do this, then you will see it's x, y, z times 0 minus z and y, right? And how much is that? So that will be zy minus yz, but that certainly is 0, right? Because those are real numbers, so they are commutative. Even if they are complex, they would still be commutative. So indeed, this whole thing goes away. That is 0. Okay, because the sum of the terms, all of the terms are 0. And guess what? The second term is also 0. And that's exactly because of what we have shown here. That's exactly this. Okay, which follows from the rotation invariance of the potential with respect to the x-axis. Okay, so I didn't redo this derivation because that's what we did the last time. How from this you can get this. Okay, but let me at least copy this here. And paste it here. And if you look at it, look at this, it's just transposition away from this term, right? So if I transpose this, even with the minus, right? Actually, that's why it was good that we did not forget about the minus, right? Because the S1 transpose generates minus S1. So this is exactly equivalent to this, and that is 0. And that's a consequence of this assumption of the rotation invariance of the potential with respect to the x-axis. That's our example. Okay. So I can conclude that this whole thing is indeed always 0 as long as this assumption is satisfied, and therefore L1 is a first integral. And that first integral is called the angular momentum. In this case, the angular momentum with respect to the x-axis. And now we know, and from what we said before, the first integrals mean that the quantity is conserved during the entire motion. So that this tells you that if this is true for your potential, then this L1 function, if the xi's and vi's, the positions and velocities, they will vary during the motion, but they will vary in a way that this L1 remains constant. And that's a thing you can observe in the real world. The textbook example of this, you might have had it in some physics class, is a figure skater. Figure skater rotating, doing like pirouettes or something. Maybe I can, well, this is going to be a little embarrassing, but I can attempt to kind of draw it. So if you have like a figure skater, like rotating, and the gravity, of course, points in this direction. So this assumption is satisfied. That's very important. Okay. Otherwise, the momentum would not be conserved. Okay. And look at this funny form of the angular momentum of the angular momentum. It's a product of some components of the axis, so positions, with some components of the velocities, and then all summed together. Okay. And there's this funny effect which you can observe if you watch like a figure skating competitions or physics instruction videos, is that if this figure skater starts rotating, it has some angular momentum. And the funny effect is that if she extends her arms and a leg like this, then what happens? Have you seen this?
Turns more slowly.
Exactly. That the angular velocity of that rotation slows down. Yeah. And why is that? That's because the angular momentum needs to remain constant. And basically, by this lengthening these limbs, we basically increase those axes. So if this is to be constant, then the V's have to decrease. Okay? And the other way around. If the axis gets smaller, then the V's needs to be larger. So then the figure skater starts spinning faster. Okay? It's a little bit, and wait, I'm not doing this in detail, and then there is a moment of inertia and all those things, but this is really the key idea. The key idea is that this quantity will be conserved, so if one changes, the other one needs to change correspondingly so that this thing can remain conserved. And this is something you can observe in the real world if these assumptions are satisfied. Yep.
So when we're saying this only holds when potential doesn't change with position, I mean instantaneously, right?
With rotation, yeah.
Yeah. Because like if you had a wheel and you point it such that its axis is somewhere off the direction of gravity. I mean, if it was unbalanced, then it would gain, momentum. The weight would gain momentum on the way down, but then lose it on the way up. And so you're not like making momentum, but still instantaneously, it's not momentum is conserved. Is that?
So your example is like a rotating wheel, but it's not rotating about an axis parallel to the gravity vector.
Yes, right.
So
I mean, you're not creating momentum overall, but instantaneously, like for example, like as the wheel is spinning, like one side of the wheel is losing potential, on the other side is gaining it, and there really isn't any overall change in momentum. But if you had an unbalanced wheel and the weight on one side would go faster, but then it would lose its, then it would gain its potential again on the other side. So we're only talking instantaneously.
We're only talking about a fixed axis. So if it's rotating about an axis, clearly the momentum is not going to be conserved about that axis. But even if it's doing that, the momentum about the y-axis of the wheel should be conserved.
Okay.
So all of these derivations are, he did it for the x-axis, but you can also do it for any arbitrary axis. And
right.
If there's no, let's say there's no gravity, right? There's nothing, it's just sitting there. Then it's going to be rotationally invariant with respect to the center of mass, right?
Yep, that's actually a great thing to bring up. So all this entire example I did was just an example, okay? It's not like a complete discussion. That's just an example of conservation of angular moment with respect to the x-axis, okay? That's just a special case, really, right? That's the example of the figure skater. Then you can actually start thinking what happens in general, right? In more general configurations, right? But maybe this is not satisfied, right? Or maybe it is satisfied in a different way, right? But like another example would be that if you have if the potential is completely rotationally invariant, rotation invariant with respect to all possible rotations, all of the SO3 group, okay, then this x-axis angular momentum is conserved, but also the y and z, okay? So there is more conserved quantities in that case, okay? So I don't want to turn this into like analytical mechanics class, but I will at least give you a pointer of how the general result looks like, okay? So here I basically just illustrated it by a few examples. And the general result is called Noether's theorem. And that's his historical aside. Now we are moving to the 1900s. This was done in, I think, around 1915 by the female German mathematician Emmy Noether. And what she figured out is basically, and you can probably start seeing this already, that there is a pattern, right? That invariance of the Hamiltonian of the potential in our case implies some conserved quantities. Okay, so the Nether's theorem is a general way to construct these invariants or these conserved quantities, first integrals, from symmetries of the Hamiltonian in general. It gets even much more general than the cases we were considering here. Okay, so let me just give you the, I guess, and that will also serve as a nice summary. So what we have seen that the time invariance of the potential, that implies energy conservation or Hamiltonian conservation. Hamiltonian is the energy. And that's simply due to our assumption that I made here that the potential depends only on x, okay? If the potential was allowed to depend on t, then the energy would not be conserved in general. Then what we have also seen, the translation invariance, translation or shift invariance of E implies linear momentum conservation. And here the linear momentum can have like different meanings depending to what exact translations is the potential invariant. Okay, there is like no one canonical linear momentum, like one canonical energy, but there are different types depending to what exact translations is it invariant. And then there is rotation invariance, and that implies that angular momentum is conserved. Okay, and the general theorem that says it so these are just some examples of symmetries of the potential or invariance of the potential, and each of them has a corresponding conserved quantity, and the general statement is the Nether's theorem. So that was just to wrap up the conservation part, and now I would like to move on another last invariant of motion, but one that's very important in a numerical integration. All these things, by the way, are also very important in numerical integration because these are actual very, very observable qualities of the motion, right? Like the spinning of the figure skater. If you're actually simulating something that looks like a figure skater, then you want to get these like global overall qualities of the motion right? So you get nice realistic animation. And another property that's also conserved, but in somewhat different sense, is symplecticity. So that's the last invariant of motion I would like to talk about. And the slightly tricky thing is that it's a different type of motion invariant than the conservation laws we talked about before. Okay, so the conservation laws we talked about so far, the momenta and energy, they basically talk about quantities over time, conserved over time, during the duration of a motion. Okay, that's the idea of the first integral. That's a function that does not change its value as the motion keeps going on indefinitely. Now, symplecticity, it's a different type of conservation. That's a type of conservation over phase space. Okay, so what do I mean by that? Oops. Specifically, what do I mean by that is that now we will study what the motion will do if we start changing the initial conditions. Okay, so before the contract was that we are given Z0 initial conditions, and we are solving essentially an initial value problem. We had to find a function Z which was mapping from time to the phase space to R to N, which satisfies the Hamilton's equations. And the Z0, of course, equals these initial conditions. That is an initial value problem, right? So the contract was, I give you initial conditions, find me the solution of the motion, okay? And these conservation laws we discussed so far, they tell you what properties the solution has to have, okay? So I guess another historical remark I found in some book is that these conservation laws were, and the first integrals were found as a byproduct when people are trying desperately to solve the equations of motion analytically. That's before computers were invented. That was kind of the only way. Like think about like writing down functions and sines and cosines and try massaging it to get something out of it. And people quickly realized that this is only possible only for very few cases. Okay, so now all non-trivial cases are done using numerical integration, and that's essentially why we are also doing all this. We're trying to understand what the real motion does so that we can replicate these properties in numerical integration. All right, so so to understand symplecticity, we need to take a little bit different view on the motion. Okay, so this is what we looked at it before, but now let's take a slightly different view. Now let's say that I assume that I fix some amount of time t, okay, like 1 second, for example, okay. And what I will be interested in is studying how z of t changes if I change the initial conditions. If I change z 0, okay? And by change, I mean imagine like a small perturbation, okay? So imagine I make a small perturbation to z0, and I will want to know what effect this small perturbation will have after time t. And imagine for a moment that the t is fixed to like 1 second or something, okay? And the entire point of symplecticity is that this change cannot be arbitrary. This change needs to observe certain geometric principles, and these geometric principles are what is called symplecticity. And again, I'll give you the hard math on it. I just wanted to give you the intuition first. So I guess as a starting point for the intuition, like think about the 1D case of the harmonic oscillator. That's what we started with, right? That had only 2-dimensional phase space with positions and velocities. And for every initial condition, the harmonic oscillator was like spinning, right? Or was bouncing back and forth, kind of like this, right? But the motion, of course, depended on the initial conditions, right? So now I'll be studying the question is, for example, how the harmonic oscillator, what result it will have after 1 second if I change the initial conditions. Okay, so if the initial conditions were position was 1, velocity was 0, okay, so after 1 second it moved somewhere, right? And now I'm asking where it will move if I change it from 1, 0 to like 0.99 and velocity like 0.01, something like this. How can the result of the motion after 1 second change? Okay. All right. So this makes sense intuitively. That's really the idea of symplecticity. So now we need to again make it formal and make it mathematical to move from hand waving to mathematics. Okay. So first, let me change the notation slightly so it's a little bit easier to write. So let's call the initial condition z0. Okay, it's still a point in the phase space, so it's a 2n-dimensional vector. So this is initial conditions. This is really just me being lazy to write these brackets, so I just put the 0 in here. There's actually another reason for it, which will be obvious in a little bit. And then we can call the state after time t, we can just call it zt, okay? So again, the same thing as before, we would write z of t, okay? So these parentheses, they mean the dependence on time. But the thing is that now I will study the dependence on the initial conditions, okay? So I will actually view this zt, and that's really the key to understanding this, as a function of the initial conditions, as a function of the z0, if you will, okay? So I will assume that the t is fixed, okay? So assume that, for a moment, assume that the t is fixed. Eventually you'll have to unfix it and see what happens if you change also the time, okay? But for now you can pretend that the time is fixed, and we only change how the resulting motion, how the resulting state after time t depends on the initial conditions. Okay, so the input is the initial conditions, the z0. The output is the zt value, the state after time t. Okay, and I'll call this function zt. All right. It's a little bit tricky. Feel free to ask if something is unclear, but I guess once you wrap your head around it, it becomes trivial. And the next thing we will need is a mathematical tool, some mathematical tool to study how zt changes if we slightly change its argument. Okay, so I could write it like this. So the zt is a function of the initial conditions, okay, a function of z0. And let's say that I do some small perturbation p to the initial conditions, okay? So the z0 is a 2n-dimensional vector. The small perturbation p is also a 2n-dimensional vector, okay? And what is the mathematical tool to approximate this change? I guess we had this before, right? There is a, right, what I want to do is a first order approximation of this. So if I want to approximate this to a first order for arbitrary functions at t, it wouldn't have to be anything to do with physics or anything. So this is a function from 2n to 2n, right? So it's a vector function. So what is the mathematical tool for studying, at least approximately, how do the values, the output of the function change if I slightly change the input arguments? And we had this before, just now we are looking at it from a slightly different angle. Sorry, Junior?
Taylor expansion.
Exactly, Taylor expansion. So the first term of the Taylor expansion is going to be just this, and that will be like a 0th order approximation, right? And if I want to bring it to a first order approximation, what is the next term there? So this thing does not take the perturbation into account at all, right? So this would be really good if the perturbation was like extremely small, right? The perturbation is slightly larger, then I want to add another term to the Taylor expansion, but it's Taylor expansion of a vector function, okay? So what is that second term? It's a gradient, but it's a gradient of a vector function, so it's called Jacobian. I mean, you can call it gradient too, it's just like a silly terminology. I usually call it the Jacobian, but if you call it gradient, that's fine too. It's a gradient of a vector function. So most importantly, that's a 2n by 2n dimensional matrix, which also depends on the z0, okay? Which I usually will not write always the z0 there. We'll just understand it depends on the state where it's evaluated, and it's multiplied with the perturbation vector. Okay, this is the 2n by 1 perturbation vector. Quick syntax check, that's a 2n by 1 thing, so this is all cool, okay? That all works. So this is a way to mathematically say this is the first order approximation of this general nonlinear zt function, okay? And the Jacobian can be understood as a local linearization of the function, okay? Just to be clear, what is in general, just to, if we have a function just from Rn to Rn, just to make sure we are all on the same page, then the Jacobian of the function f is a matrix of the first derivative of the function, okay? All the partial derivatives. So I take the first component of the function. It's a vector function, right? So the output has n components. Here it means I take the first component, I differentiate by x1, and I keep doing this and differentiate by all the input components up to xn, okay? Here I do the same thing for f2 and so on up until I get to fn, and I differentiate it again first by x1, then by x2, and so on until I differentiate the last component by the last variable xn, okay? So this would be an n by n matrix, that's the Jacobian. If this was a height field, or no, it was a vector field, if it was from R2 to R2, then you can think about it as fitting planes. that best approximate the actually no, it would be better from R2 to R1. Either way, at any rate, it's a local linearization of that function. Okay. And what symplecticity is? Symplecticity is a constraint on the Jacobian of ZT. That's what symplecticity is. Okay. I can take this away. That's just to refresh our memory on what is the Jacobian. And here I can finally write the definition of what symplecticity means in mathematical terms, not in philosophical terms. So symplecticity means that this thing here, the gradient of the ZT function, okay, so I copy that, the gradient of the ZT function evaluated at some state as Z0. If I transpose it, multiply it by our old friend, the J matrix, and I multiply it again by the same Jacobian, ZT at Z0, that the condition says that this must be equal back to J. Okay, and that needs to hold for every Z0 from our phase space, in our case 2n. Okay? So just to make sure I'm not smoking crack, this is a 2n by 2n matrix, right? Oh. This is also a 2n by 2n matrix. That's the Poisson matrix from the Hamilton equations of motion, okay? This is also 2n by 2n matrix, of course, and this is also 2n by 2n matrix. So syntax checks out, okay? And what this is equality between two matrices. The J is always the constant matrix, right? Just to refresh your memory, the J was this matrix, right? Minus I0, 2n by 2n constant matrix, okay? The Jacobian of the ZT function changes. It depends on the initial conditions. Okay, that's really the thing. And of course, this also has to be true for any t, right? We assumed here that the t was fixed, but it's true for any t. So this is actually also true for any time t. Okay. So what the symplecticity is, it's a condition on the Jacobian of the ZT function, which tells us how the motion after time t changes if I change the initial conditions. In physics, you might have heard these results in a slightly different language. There's a thing called Liouville theorem in physics, and that's exactly the same thing, just in a slightly different formalism. They talk about distributions and stuff, but all right, so I claim this is true for any motion, okay? For any ZT that solves the equations of motion, if I now forget about the t being fixed, right? If t is no longer fixed, then I can talk about the ZT for varying t solving the equations of motion, right? And I claim that this is true, so I need to prove that. So how do we prove this? So let's look at a proof. I think I will need another page. So let's grab this. Oh no. All right, so how to actually prove that this is true? So now I need to start, so now the assumption is that ZT solves the equations of motion, that ZT actually is a valid motion for the initial conditions at 0, okay? So first of all, we need to, so I guess there are like two cases. The first case is really simple. That's for time equals 0, okay? That's the trivial case. But it's kind of fun to think about it. What's the gradient of the ZT for t equals 0? What is the Jacobian of the ZT function if t equals 0? Or what is the ZT function for t equals 0, right? I said that the function is like parametrized by t, so you can imagine I can plug in whatever t I want. So if it happens to be 0, the simplest possible case, usually you don't travel against time, right? So the 0 is the smallest it gets. That's a trivial case, okay? In that case, this function, well, what is the zt function for t equals 0? It doesn't go anywhere, right? There's no time to move. So what does it return? Exactly, Brent. It returns exactly the initial conditions. And a function that just returns its argument is called identity function, okay? And the Jacobian of an identity function is identity matrix. So in this case, this Jacobian of zt is identity, okay? And sure enough, if you plug it in there, then you get identity times j times identity. Well, sure enough, that is j, right? So that's another like sanity check, right? So that's good. So at the beginning, for t equals 0, it's true, okay? And now to establish that it also works for any other t, we will do our usual trick. What we're gonna do, we're gonna time differentiate, okay? We are gonna time differentiate this expression on the left, and if we can show that this derivative will be 0, then it means it doesn't change. That means that it stays this j, and we will be done, okay? We will have proven this matrix equality, the symplecticity. So let's do that. It's a kind of fun thing to do. It's another calculus exercise. So we time differentiate this expression. So forgive me not writing there and I will not even write these parentheses. Forgive me to not writing there the z0s. We'll just know that the zt always depends on them. The j does not. So I'm differentiating this expression. This was not supposed to be there. So this differentiates using the product rule, right? So that means that I first differentiate this zt by time. So let me just make it as a dot, okay? I guess I could have written dot about this whole thing instead of the partial, but that's just a notational thing. And I just copy this. Plus the Jacobian of zt transposed times j times the Jacobian of zt time derivative. Okay, that's the product rule for vector functions. Okay. And now what we need to figure out, what are these, what happens to the zt if I differentiate both by type, that's this little dot, that's the time derivative, and by phase space. That's this. So this Jacobian, that means with respect to the phase space. That's what I meant by respect to the z0. That's why I actually changed the notation so that I put the t here, so it's kind of less confusing what you're differentiating with respect to. Okay, this notation's still not perfect, but that's a problem of the notation. So what we know from the equations of motion is that t solves the equations of motion. We know that this is true, right? It's about the time that at some point this will probably stop recording, so remind me that when that happened. Those are the equations of motion, and that's what we assume is satisfied, right? The symplecticity, of course, the idea this is true if the zt satisfies the equations of motion, so that's our assumption here, that the time derivative of zt, now we of course assume that t varies, right? So this is just a notation to sort of separate the differentiation from over time from the differentiation over phase space. That's what these nabla operators mean, okay? So those are just Hamilton's equations. And what I need to do now is to differentiate it also over phase space, okay? So differentiating both by time and by phase space. That's actually not that hard. All you need to do is the chain rule, right? So this was the gradient of the Hamiltonian. And if I'm differentiating that, that becomes the Hessian of the Hamiltonian, okay? The Hessian of the Hamiltonian is the matrix of second derivatives. And to complete the chain rule, I need to differentiate whatever was inside. Now again, remember, now I differentiate with respect to phase space. So the zt gets differentiated over phase space. So I have to put there the Jacobian of zt. Okay, so that's just a vector application of the chain rule. Okay, so let's just check the dimension. This is 2n by 2n as always. The Hessian is a matrix of second derivatives. Okay, so that's also a 2n by 2n dimensional matrix. Okay, do you know do you know the property of the Hessian matrix? The Hessian matrix is always symmetric. Okay, and that's because it doesn't matter if you first take the partial by x and then by y, or first by y then by x, you always get the same result. That's why the Hessian matrix is symmetric. Okay, so that's just kind of brushing or dusting of our calculus, I guess. You probably have this better in your memory than mine. It's been like 15 years since I had calculus, but these things are standard. And this thing, of course, is our Jacobian, so also 2n by 2n matrix, right? And if you differentiate by time, the time is just one variable, so it doesn't change the fact that this still is a 2n by 2n matrix, okay? So this is, again, a matrix equality, okay? So what we're gonna do now, we are gonna plug this expression in here, okay? So that means that I need to transpose this entire thing. So let me take this, transpose it, and plug it in here. Okay, so I expand the first term using this. Okay, so let me do that. So first I have the Jacobian of ZT transposed. Then I have the Hessian of the Hamiltonian transposed, but I can drop the transposition because that's symmetric. Then I have J transposed. And now comes this part here, the J Jacobian of ZT, so I just copy that. Everybody got it? Was it animated well enough? So all I did was taking this and substituting it in here, okay? And there is, of course, still the second term, right? So the second term, let me write it like here. So the second term starts with, and this is this thing here. The second term starts with the transpose Jacobian, then the J, and then I just copy over this thing. Okay, so I get the J, the Hessian of the Hamiltonian, ZT, and the Jacobian of ZT. Okay? So I have some of these two terms. This is the first term, and this is the second term. And a cool thing happens now. So the J matrix, as you remember, was a 0, I minus I, 0 matrix, right? So what is J times J? That's the term we have here, J times J. So let's figure out what the J times J is. Any ideas? So I just multiply it, right? Anybody?
It's not the same. Well, 0, I, 0.
Almost. You can say it in 2 words, by the way. Oh, yeah, almost right. I mean, so that's just matrix multiplication, right? I take this row times this column, I get minus I, right? That's what comes here. Then I take this row times this column, well, that's 0. Then and so on, right? And this is minus identity. 2n by 2n. I can write it like this, like minus I. Some people write like 2n and n here to kind of make it clear what the dimensions are, but spare me doing this and just infer the dimensions. So that's what J is. Now what is here? Here we have this guy JTJ. All right. So what is JTJ? Well, that's a similar thing, right? Let me do it slower. So first I transpose. Actually, it's kind of easy, right? If the J matrix is also antisymmetric. So J transpose is minus J. So JTJ is minus JJ. So that means this must be what? Identity, exactly. If you wish, 2n, like a 2n by 2n identity matrix. So that's quite beautiful because the JTJ we said is the identity, JJ is minus identity. So guess what happens here? So this is the Jacobian transpose, this is the Hessian, this went away, right? Since it's identity, I might as well not have it there. This is the Jacobian of ZT. And this is the same thing except for a minus, okay? This minus thing, or watch this minus thing, okay? So what is it altogether? 0, exactly. And that's exactly what we needed to prove, right? The time derivative is 0. That means that this quantity here, this thing here, for any z0, does not change with time. That means it has to keep the value, by value I mean the matrix value, it had at time 0, which was j, so this is indeed true. Okay? So that shows you that for any solution of the equations of motion, this symplectic condition is always satisfied. Okay? And it's a kind of a strong restriction if you think about it, because this entire thing, that's a matrix equality. Okay? The thing on the left is a 2n by 2n matrix, and this matrix changes, right? The Jacobian, of course, changes depending on z0, right? For every z0, except for some trivial cases where it happens to be constant. But in general, this changes for every z0. But for all of them, it needs to just evaluate to the same matrix J. Okay. Now, what does it mean intuitively is slightly tricky. But here is a way I can make it slightly easier to understand, at least partially. Okay. Because, and let's see if I still have it in my clipboard. Oh, I need to do this. Paste. All right. And here is one cool thing that follows a consequence of symplecticity. Let's take the determinant of this. You know that the product rule of the determinant, right? So you know from linear algebra that the determinant of matrices AB, which can be multiplied together, is equal to the determinant of A times the determinant of B, right? What is the determinant of J, by the way? The determinant of J, what is the determinant of J? You don't have to compute anything. It would be like, I guess, a simple determinant exercise. But from what we said last week, you can immediately tell me what a determinant of J is. Because we said what J is geometrically. I? No, it's a real matrix, right? So the determinant must be a real number. No, determinant is a scalar. No. I guess the next guess must be correct. 1, yes. The determinant of J is 1. And that's because J is a rotation. Okay? Rotations have determinant equal 1, right? So rotation is because the product of 2D rotations, each of the 2D rotations is determinant 1. Again, by the product rule, you could, for example, argue that the determinant is 1. You could argue many other ways too. It's such a simple matrix, right? So if I take determinant on both sides of the equation, then I will see that the determinant, so also you know that the determinant of the transposed matrix is the same as the determinant of the matrix non-transposed, right? We are, of course, talking about square matrices, but that's the case here, okay? So this boils down to the determinant of ZT, the determinant of J, determinant of, again, the Jacobian of ZT, and that needs to be equal the determinant of J. So I just applied the product rule and put determinant on both sides. I know that the determinant of J is 1, right? So this implies quite clearly that the determinant of the Jacobian of ZT, again, there is hiding like a little Z0, so for any Z0, yeah, that must be a plus or minus 1. Okay, because this thing squared must be 1, so this could only be plus or minus 1. Okay, there's no complex business because this matrix is real, so the determinant is also going to be a real. Okay, no funny complex eigenvalue kind of business. Is it possible that this would be minus 1? The answer is no. It's impossible because remember, for t equals 0, we know what the Jacobian of ZT is, right? It's the identity matrix. Well, the determinant of the identity matrix is 1, okay? And the motion changes continuously, okay? So this determinant of ZT must be a continuous function. There's no way it could at some point jump to -1. That would be a discontinuous change. So this -1 is actually impossible. So it has to be the case that the determinant of the Jacobian of zt is always 1. Okay? And that gives you an geometric interpretation of the symplecticity. That means conservation of volume in phase space. You can say that the zt function, that's the function from the initial conditions to the phase space state after time t, you can say that this preserves volume in phase space. Actually, we can say more. We can say volume and orientation in phase space. Okay? So the orientation means that's the determinant is 1. What I meant, orientation would not be preserved. At some point it flipped. Okay? By the way, this is very closely related if you are doing medical imaging, if they're talking about diffeomorphic maps. This is very closely related to it. That's the orientation preserving. This thing cannot fold over on itself. Let me tell you, what does it mean intuitively, the volume preservation? If we go back for a moment to our 1D case, where the phase space was 2-dimensional, okay? You remember that I used to draw it like this, like the position and velocity. Imagine like the harmonic oscillator kind of thing, right? And that motion, so this is like the space, this thing is the space of all the initial conditions. And then the motion after some time, let's say t equals 1 second, then it maps somewhere else. Okay, so if I have some initial condition z0 here, that gets mapped to some zt over there. Okay, if I have another z0 here, that gets mapped, I don't know, for let's say here. Okay, this is where it started. This is where the motion ended after time t. Okay, again in the exact solution. What symplecticity says is a beautiful thing. It says that if you take an area, if you take some closed set omega, then this entire thing, all the initial conditions inside here, they get mapped somewhere. Okay, so this will be the zt of omega. Okay. And the fact that the determinant of the Jacobian is 1 everywhere, that implies that the area of this thing, of the zt omega, must be exactly the same as the area of omega. Okay, that it's area preserving. So that's a geometric constraint on the motion. Oh yeah, by orientation I mean that this determinant must be +1. So if you look at, so let's take a look at this initial condition, right? I can give it like a little bit like little coordinate axes here, right? So this will be like a little x and little v, if you will. So this thing like might rotate like this, right? Even actually with the harmonic oscillator when it was just spinning around, right? So this would be like little x and little v, okay? So you can imagine this little element has an orientation, right? Because I can rotate from x to v using the right-hand rule, okay? And the orientation preserving means that here I can also rotate from x to v using the right-hand rule, okay? By the way, this would not have to be 90 degrees. It could also be, this could get skewed, right? This could get skewed like this and scale. This could be my x, this could be my v. Maybe a better way to think about it is like, think about like an infinitesimal element, right? Like some very, very small square kind of thing with some 2 axes here that can get mapped somewhere, and this element can get squished. It can get squished even like a lot. It can get squished to something else, right? But the orientation preservation means that I can still do the right-hand rotation from x to v. Okay? You do know what transformation would violate this, would not be orientation preserving? all these like rotations and scaling and translation, they are all rotation preserving, speaking of the basic transformations, right? But there is one elementary transformation which is not orientation preserving. It's the mirror transformation. Okay, if I took just very quickly, because we need to finish, if I have like a little house here, right, and I say this is a mirror transformation, and the house gets mirrored, let's say the chimney here, it gets mirrored like this. So this thing actually flips the orientation. So this symplecticity, this implies it must not be flipping. The orientation needs to be orientation preserving. All right. So unless you have any more questions, we can stop here. And it looks amazingly that the recording survived.